is Ryan Campbell, and I'm going to teach you about virtual knots. First off, what is a virtual knot? A virtual knot is very similar to a classical knot, which we have been studying all semester. The difference between a classical knot and a virtual knot, though, is that virtual knots can have some virtual crossings. Virtual crossings do not actually exist, hence the name virtual. We get virtual crossings by drawing non-planar graphs on a plane. So if you think of a sphere or a torus or any of those three-dimensional shapes, we see those virtual crossings as what is on the other side of that three-dimensional object. What I have here is a CD and then a clear version of a CD. We can see on this one, picture this as a torus but flattened. We see this knot that goes around, and at one point through the center of this torus, the string or that strand goes underneath the torus and comes back out here. If we visualize this clear though, we have the same knot, but over here we see that that strand crosses underneath this strand. We know from here that those two strands do not actually cross because we can't see it. There is some space in between them, but over here it looks like they are actually crossing. So all of these are called classical crossings because they all happen on the same side of that plane, and over here this is a virtual crossing. Here are some diagrams of virtual crossings. We have the two classical crossings on the left and the right. These would be on the same side of the plane. And then for virtual crossings, we see the diagram has just an X instead of a gap like we normally draw. And in addition to making it just an X, we also draw a tiny circle around it to show that that is unnatural. It's not a normal classical crossing. So what types of moves can we actually do with virtual knots? We can do all of the normal classic Reidemeister moves, Reidemeister 1, 2, and 3. Notice that either direction, we have a classical crossing, and then no crossing at all, classical crossings. All three of these are classical crossings in that Reidemeister 3 move, and they remain classical crossings after the move as well. So we neither create nor remove virtual crossings when we do those classical Reidemeister moves. We also see the virtual Reidemeister moves. We can do the virtual versions of those moves as well as the classical versions. And soon I'm going to show you how we can actually do those. We see the virtual Reidemeister moves over here. We see it's a virtual crossing because of the X and the circle, and we can remove that virtual crossing. Two virtual crossings, can remove them using a virtual Reidemeister 2, and if we have all three virtual crossings as we do a Reidemeister 3, we will still have all three virtual crossings at the end. Also, these are the ways that we note that they are virtual crossings, virtual Reidemeister moves rather than classical. We put V of R1, or we can use the symbol omega, and we can put the little prime symbol next to that, and then put a 1. A classical Reidemeister would just not have the prime. Another new crossing that we are going to get is a semi-virtual move. So our semi-virtual move has some classical crossings and some virtual crossings. In fact, we have one classical and then two virtual. And then when we do what looks like a Reidemeister 3 move, we have to move the one that is up here down to over here. Okay? So those two virtual crossings move down to here. The semi-virtual move is a version of a detour move, which we are going to see in the next slide. So a detour move, we have some kind of knot portion over here where all of these pieces would be connected. And this portion over here would be on the other side of the plane. Now that makes these three, or as many as we want, just all in a row, all of those would be virtual crossings. So if we have that string of virtual crossings, we can actually take this piece right here, keep those two endpoints exactly where they are, and we can move that middle portion of the string completely in front of the knot or completely behind the knot. Because remember, this part is either on the front or the back of a sphere or a torus or something, and then this is on the other portion. So it's kind of just like turning the sphere. Think about turning a beach ball, which colors would be in front of what other colors. It just completely changes as we move. And that detour move is actually how we get the virtual Reidemeister moves. Okay, I'm going to show you how we get the Reidemeister 1 move and Reidemeister 2 out of the virtual crossings. So let's start by doing a Reidemeister 1 virtual version. So we have a sphere, and this piece is in front of the sphere. This piece is on the back side of the sphere. There are no virtual crossings because nothing from the back crosses over anything, crosses anything that is in the front. But what we are going to do is create a Reidemeister 1 type move, just like a half twist. And I'm going to do that over here. I'm going to do that by twisting this piece right here. So that can stay. This piece is going to move slightly over this way and come back to here. So we've just done a little twist. So this piece is still on the front, this is still behind, but now it looks like that strand that's on the front of the sphere is actually crossing over the one that's on the back, which is not actually happening, but that's what it looks like. All right, the next one we are going to show the virtual Reidemeister 2. So this would be VR1, and this is VR2. Okay, a Reidemeister 2 move normally looks like this changes to this, and of course, one of those crossings can be in front or behind. Over here, we are going to make it so that, and it doesn't matter which one is in front or behind, which one moves. I'm going to move this piece, just pick it up, and scoot it this way, so it goes up this direction and then comes back. Okay, so now it appears that this piece from the front is actually crossing over the part that's in the back of the sphere, though they are not actually crossing. Okay. So we would show that this is actually happening by drawing this knot. Okay. Looks very similar. Of course, we have a little bit of planar isotopy going on. This crossing is staying the same because it's a classical crossing. There's no actual crossing going on over here. It's just curving around the back of the sphere. Again, curving around. But over here, this is where we get that virtual crossing. The forbidden moves is another difference between classical knots and virtual knots. The forbidden moves looks a lot like a Reidemeister 3 or a virtual Reidemeister 3, but it's not actually what that is. Okay? We can see this strand crossing over this virtual crossing and then ending up over here. Okay? Or, of course, under crossings, traveling underneath and coming back this way. We have a problem, though, whenever a regular strand, classical crossings, whenever that's trying to cross over a virtual crossing, because we're not sure which of these two pieces is on the front of the sphere and which one's behind? We don't know. Okay. So let's take a look at that. This strand right here is on the front of the sphere. This strand goes from the front to the back of the sphere. So when it goes to the back of the sphere, it's actually crossing over this piece right here. And then this piece is also on the front of the sphere, and it crosses over both of these strands as it's over here. Okay, if we want to take this piece and cross it over this virtual crossing, that's what's happening, okay, because currently it is on this side of this crossing, so it's crossing over these two parts, okay? We want it to move over here. If we move that piece over to here, it ends up crossing at those 2 points. This strand was in front of the sphere, so we realize this piece right here, this piece has moved over here, it's moved in front of this strand, but this piece was back on the other side of the sphere, which makes this another virtual crossing, okay? Now, this could actually occur if either one of these two pieces is on the back side of the sphere, and the problem is that we don't know which one it is. So we can't have a whole, like a steady rule saying that when we move this over to here, that this one is a virtual crossing and this one's a non-virtual crossing, just a normal one, or that this one would be virtual and this would be a classical crossing. We can't tell, and that's why it's forbidden. So now we're going to talk about this theorem that comes from virtual knots. The theorem says that if J of L is not equal to 0, then L is not equivalent to L star, where L star would be the mirror image of the virtual knot L. Okay. Also from that theorem, we get that if J of K, the knot K, is not equal to 0, then K is not equivalent to a classical knot, which means that K would have to be, of course, a virtual knot. So let's start by talking about what this J polynomial is, or J function is. So J of L, a knot L, equals the writhe of only the odd crossings of L. Okay, well, what do we mean by odd crossings? Let's take a look at this classical knot M, okay, especially this crossing over here. From the first time we touch this crossing, traveling around in a fixed direction, we cross over 1, 2, 3, 4 crossings before finally making it back over here. So this crossing would be called an even crossing because we have crossed over or under an even number of crossings. Earlier in this course, we have shown that a classical knot can only have even crossings. It can't cross over an odd number of crossings along the way. Okay, so that means that J of M, if M is a classical knot, it's going to equal 0 because it's the writhe of the odd crossings. Well, there are 0 odd crossings in a classical knot diagram, so the writhe of nothing is nothing. We have 0. Okay, well, our goal actually is to talk about when the writhe is not 0, so that means that J of L would have to be the J function of a virtual knot. So both of these would have to talk about virtual knots. So let's look at virtual knot K. Okay, the mirror image of the virtual knot K is K star. Earlier in this course, we have also shown that the writhe of K star is the opposite of the writhe of K. Okay? We get the mirror image by changing all of the crossings, so that, of course, changes how all of those writhes work. Anything that would be positive would turn negative, anything negative turns positive. Okay? So that means that since K and K star have the same number of odd crossings, J of K is going to be the opposite of J of K star, okay, because their rides are opposite, but they have the same number of odd crossings. Okay. So let's bring that back over to the theorem. If the J of L is not equal to 0, then L is not equivalent to L star. Okay. Well, looking over here, J of K is the opposite of J of K star. The only time that is true, if these are the same, is if J of K and J of K star are both 0. Okay. Otherwise, they're just opposites of each other, so they could not be the same if they were not 0. So this part of the theorem has been proven. This statement over here, J of M equals 0, is actually the contrapositive of this statement over here, which means that we have proved it. So we know that if J of K does not equal 0, then K is not equivalent to a classical knot. Everything that we've talked about with these even and odd crossings is actually still a subject of research in knot theory. And obviously it has to be with virtual knots because those classical knots only have even crossings. The odd crossings actually help us find some distinct invariants for virtual knots. So I hope this has inspired you to study virtual knots.